Hello everyone, and welcome to looking at using inverse norm on your calculator. We looked at a few conceptual questions last time, but we're going to be aiming to go through some more in this video. So part 2, the last part, we're going to be looking at a few more challenging ones, and we're going to be looking at things like electricity bills, and we're going to be looking at a few more contextual problems. So again, using inverse norm. So in order to do this, what we first check out is our problem and break it down into simple logical parts, because of course we need to interpret what it means contextually and understand what exactly they are asking. So the amount of money people spend on their electricity bills is normally distributed. That's good because we're looking at normal distributions. If it was something else, then it might not be so good. Because it's normally distributed, we can find out a bit of data using inverse norm. So 20% of homeowners spend more than $125, so greater than $125, on electricity per fortnight. So if we were to work out where this fits on our distribution, we can simply remember the parts of the empirical rule about how the distribution is broken down and approximate where our value of k will be. Of course, k will separate the 80% who pay less than 125, because these people pay more than 125. So 80 will separate the people who pay less than 125, and 20% will show those who pay more than 125. So after 3 standard deviations, that's where 0.15% of the population lies. You may remember that I covered some things on normal distributions and empirical rule a few times before. We have 2.35% that lies there, and we have, of course, here 13.5%. And this here makes a sum of 16%. So now that we know that, we can simply go, okay, if that's 16% and it's going to be 20% and it's going to be to the right of the mean because it's people paying more, then we can approximate that it will be close to 1 standard deviation right of the mean, and it's going to be closer to 1 standard deviation right of the mean because there's only 4% difference under the curve there to make up our 20, and also because 34 fits in here and it's closer to being at 84, which is a value 1 standard deviation, compared to just 50%, which is at there. So of course that k value represents $125 per fortnight that people spend on their electricity bills. The price of electricity, of course, is going up. It's getting quite high. It's pretty expensive these days. And of course, because inverse normal looks at the proportion of area below this value of k here, below the boundary between that 20% and that 80%, we of course know that when we put our area into our calculator, we're going to need to put in 0.8 because that's the area below our value of k. And because we don't actually know our mean, that's what the question actually asks. It says we have a standard deviation of $5 and $125 is spent per fortnight to separate those two. It asks us what the mean amount is that homeowners pay, and it says here per quarter. We're looking at per fortnight here, as you can see. But of course, if we look at the mean per fortnight, it will also be the mean per quarter as well, because it's just a longer period of time. And the last bit of the question says to assume 6.5 fortnights in a quarter. So we've broken down the question, we've got an idea of how invnorm fits into here, so now we can go through the process and we can say, okay, let's deduce the value of k, because that will give us an x-score, and of course because we don't know the mean, it's going to be a standard normal distribution situation, and in a standard normal distribution, when we're calculating the invnorm, we just assume that mu is 0 and sigma is 1, because that will give us a z-score. And from that z-score, we can work out the problem, because it will show us how many standard deviations it is from the mean. And then from there, we can just use the z-score formula in order to work out the mean, just by rearranging equations, the simple stuff you're probably used to. So interpreting this question is quite difficult, because when you actually read it out in full, the amount of money that people spend on their electricity bills is normally distributed, and 20% obviously pay more than that per fortnight, and it asks you the population has a standard deviation of $5, so what is the mean amount that homeowners will pay per quarter? It does sound quite challenging, and you probably don't know to use invnorm first up. Because it's giving you a proportion of the population, that's generally a good indicator that invnorm helps, but in some cases you may need to use normal CDF. So again, it's all about interpreting it. And it does take practice. So now we go to second function distribute and down to invnorm. You should remember that from the last video. And of course, I've already mentioned this, but we look at the area below the value of k. So it's going to be 0.80 as our area, not 0.20. So 0.80 with mu of 0 and sigma of 1. We paste that, we enter that, and we get a z-score. And the z-score says 0.841. That's good. 8.842 when we actually round it. So now that we've got our z-score and we understand that $125 is there and our standard deviation is $5, we can use our z-score formula to calculate where the mean will be. And this is pretty cool. Because we have the things of the z-score formula, if I just write it up here, hopefully it will jog your memory. Because we have standard deviation given in the question, because we have an x value, which is given as $125, and because we have a z-score, which we calculate using inverse norm to get a value of k by standardizing this distribution and seeing how far that value of k is relative to standard deviations, we are able to rearrange this to get mu. So, therefore, 0.842 equals 125 take mu on 5. $5 being the standard deviation, sigma. And then, what we do is we bring this 5 from the denominator on the right-hand side into the numerator on the left-hand side, and we multiply it by our z-score of 0.842, which equals 125 take mu. Mu being the mean. So let's simplify this down, shall we? So we go 5 times by 0.842, and that gives us 4.21. Therefore, 4.21 equals 125 take mu. Now we can solve for mu by just rearranging those constants. As you can see there, mu is the only unknown value, and that's the great thing about this. It's really easy to solve. A bit later on in this video, there'll be some simultaneous equations to look at, and you'll need to find both mu and sigma at the same time. And not to worry about that. For the moment, we just move mu. Because it's negative there, we move it to the left-hand side where it's positive. So therefore, 4.21 plus mu is going to be equal to 125. Okay, so now what we do is we isolate mu by saying, therefore, mu is going to be equal to 125, take 4.21, and we can do this because this is positive on the left-hand side, it's going to be negative on the right-hand side, and then we can solve for mu on our calculator, and we get a mu result of 120.8 to three significant figures. So 120.8, let's check to see if that result seems logical. So we have a z-score of 0.842, and we know our standard deviation is going to, of course, be equal to $5. So now, if we go 0.842, take 1, we get 0.158, negative 0.158, which should probably sit somewhere around about there. 0.158 negative, negative 1.58. And from that we can see it sits quite close to the mean, and that's $120, because the standard deviation is 5. And of course, the reason I subtracted 1 from that is because standard deviation is 1 in a standard normal distribution, and it's a way we're able to say, okay, if a standard deviation is $5, and that's the z-score, how many standard deviations that value is from the mean, then subtracting 1 will, of course, give us 1 standard deviation less. So $120 is very close to mean. It's negative 0.158. And 0.158, when you think about it, close to 0, isn't it? It's closer than 0.842. So hence our result is kind of logical. To the left of the mean, we have this value quite close, and it's $120, and our mean is $120.8. So we have 120 and 120.8. So yes, our result does seem logical in context. But wait, we have not answered the question yet, because the question asks us, how much does the average household pay, or average homeowner pay, per quarter, and assumes 6.5 fortnights in a quarter. So this is where we might not want to round to, say, those three significant figures. We may want to have the pure answer to ensure we get slightly more accurate results. So $120.79 is the cost per fortnight on average. So we multiply this result by 6.5, which is the number of fortnights in a quarter. And when we multiply this by 6.5, we get that the average electricity cost per quarter is, and we'll have a little bit of a drum roll if we can, just an imaginary one, because I need to actually do the calculation, but we have 120.79 times by 6.5, we get $785.14. So, and that's to 4SF. So of course we could write it to 3SF if we wanted to, in which case we could just say that and just have that $785.10 is rounded to 3SF. But I'll put the extra 4 in there, we'll be that precise. So we're using invnorm on our calculator, and we're going to look at another problem now. So we've had a look at that homeowner's situation, and I've gone through that hopefully quite logically. But now it's time to look at a slightly more difficult problem. And this time we're going to be greengrocers, and we're going to look at how much money we're making. Because of course, knowing how much money you make on average can help you predict how much you get to spend on food, and how much you get to spend on buying really cool stuff, and all of that kind of thing. So it's always good when you're doing these questions to draw up a normal distribution, or a standard normal distribution. Again, it doesn't really matter. This is just a rough drawing. Generally you draw up with a scaled set of axes, but for the purpose of this video I really don't want to measure it out because you'll probably get really bored. Yeah, I mean even more bored than usual. Okay, so in terms of the greengrocer question, what it actually asks is what it actually says, should I say, is that the weekly income of a greengrocer is normally distributed. So we're looking here at weekly income of a greengrocer. It's normally distributed, that's good, and it says that the mean is $6,100. So this is his weekly income, he gets $6,100 per week. That's pretty good. And it says here that if 85% of the time the weekly income exceeds $6,000, what is the standard deviation? So 85% of the time his income is greater than $6,000. Now just by looking at that, you can easily place where this value sort of would lie. All you need to do is say, okay, that's the mean, $6,100, and we know that obviously there's 34% lying in here, and because 6,000 is less, it makes sense it's going to be somewhere in here, and if we have a look at it, this is 34% there, and if we take the mean, which is always represented by that, take 0.34, then we end up getting a 0.26. Yep. And we know, obviously, where it's going to lie. Because, yep, in fact, 1/6, sorry. And we can say, well, there's 16% up to there. And it's 85% of the time. So, obviously, it's going to lie just after, and that should be negative, sorry. Just there. Because that makes up 15%, because the mean take 1 standard deviation. Before that we have 16%, so it's going to be just before that mean take 1 standard deviation. Okay, so now we colour in the area that we're going to calculate, and that is the area below. Because, of course, that's what invnorm does on our calculator, looks at the area below. So we calculate what that area is going to be. So, as I said before, 85% of the time he gets more than $6,000. So, it's 1 take that, which is going to give us 0.15. So, on our calculators, we go invnorm by going second function distribute, and then we go 0.15 with our mean of 0 and 1, because we have to use the standard normal distribution, because we don't know what sigma is. We are calculating the z-score. It tells us how far things are from the distribution. That's what z-scores are all about. How far is a value from a distribution? It's a score. And it's very important because we can put 6,000 as being the mean, but we can't put in sigma. So we standardize it. And from that z-score, we can use the z-score formula, as I just did earlier in this video, but we isolate for sigma, the standard deviation, and not the mean this time. But, you know, same sort of principle, just flipped a bit. Okay, so now I'll go to my trusty T84, second function distribute, invnorm, and I will go that the area is 0.15, the mean is 0, and sigma is 1. And hence we get a z-score of negative 1.036, and you know, I'll round it off to 4 there. So we get that z-score. And from this we can calculate what sigma is, again using the same sort of process. So in order to do this, we can go z equals x take mu on sigma as the z-score formula, and we can go negative 1.0364 equals x, which of course is going to be 6,000 because it gets $6,000 85% of the time, and that's going to be take, and then it's mu, which we know as being 6,100 all over sigma. Okay, and so from this, what we can do is we can bring sigma to this other side here, and we can go, okay, negative 1.0364 sigma equals, and we can simplify this, 6,000 take 6,100 is of course going to be negative 100. So now what we do, and again I've just brought sigma from the denominator on the right hand side to the numerator on the left hand side, which is what you do when you're isolating values. So we know that sigma equals 100 divided by, in fact that's negative 100 divided by negative 1.0364. And what you do is those two negatives cancel because of course standard deviation is going to be a positive result. And hence we calculate that using our calculators, and from that we get a value suggesting that the standard deviation is going to be $96.5. I've just rounded it a little bit there, but $95.60 is the standard deviation. Sorry to write it sort of in the middle of everything there, but I'm sort of running out of space. I guess we don't need those calculations anymore, but we were able to derive sigma by using the z-score formula. And let's have a little think. Does this make sense in context? If that's $1,000 here, if that's $6,000 here, sorry, and that's just over one standard deviation away, then yes, it probably does make sense that there's $96.50 in this 34% here, because just over that 34%, we're going to have an extra little bit there, reducing it to, making it 100 overall, 600 and 6,000 and 6,100, of course, there's 100 difference. So yes, it does make sense in context. Okay, so now we move on to one of the most difficult questions you'll probably come across with using inverse normal, and this one does take a lot of skill. So I definitely recommend that you take notes while watching this, because this contextual problem is quite taxing. However, if you can do it, it's a really good question, really fun, these sorts of questions, because you've got lots of processes to work through. So, as per usual, I'm going to break this down into steps that you can follow. And the first thing we do is we of course draw a normal distribution with sigma, not sigma, mu, sorry, and then mu plus sigma, got a little bit ahead of myself there, and then mu plus 3 sigma on the end. And you generally want to scale this, but video time constraints, it's already quite long as it is, this video. So now this question says, and it's very important that we analyze it correctly, but it says here, in a mathematics examination, it was found that 10% of students scored at least 80. So, 10% of students scored at least 80 in a maths exam. And it says next that no more than 15% scored under 30. And hence it asks us, assuming it's normally distributed, find mu and sigma. Okay, so we've got two unknown values, so we're going to need to think about this quite thoroughly. We're going to need to draw on these two little representations of information we have here, and then we're going to have to solve for both mu and sigma using the z-score formula. And that means generally solving using simultaneous equations. Okay, but don't panic just yet. 10% of students scored at least 80. So when we think about it, 0.15% is there, and then we have 2.35% here, and then we have 13.5%, so it's going to be somewhere in here that we have our people who got 80 or more. And then on the other side, no more than 15% scored under 30. So here we have 0.15%, then we have 2.35%, then we have 13.5%, and it said no less than 15%. Oops, sorry, I've obviously gone one standard deviation too short, so that one's 2.35, and this one is 13.5. Sorry to confuse there, I've only gone up to 2 here when I should have gone to 3, but fortunately I can't really write over there. But, yes, so it will fit in somewhere here, near one standard deviation to the left of the mean, but between mu take 2 sigma and mu take 1 sigma. So hopefully you understand that. It's reasonably straightforward. You think, oh, okay, these three here make up 16% total, so 15% must be just before the end of that. So now we use inverse norm to find both mu and sigma. And that, of course, before I forget, is 30. Okay, so how do we set up these two equations? Well, let's think about it. Remember, it's the area below, so if we were to look at the z-score for this one, there is 30 below there, so invnorm would show 0.30, and we standardize the distribution because we don't know mu and sigma, and then we get a result from that. Our second part, we would get invnorm, and this is up here, it says that 80 marks or more was there. So in this case, 20% got more than 80 marks, was it? It was, yes, scored at least 80. Or 10% of students scored at least 80. So because it's 10%, it would be invnorm of 0.90, because 1 takes 0.90 equals 0.10. And hence, because this equals 0.10, and if we were to do it the other way around, we could see that obviously it would be the area under this value here, because it takes up 10%. The area under 80 marks would be 0.90, given that the area under a curve is 1. And we standardize it, mu 0, sigma 1. And then we calculate both these results on our calculator. And what we do is we go second function, distribute, and then we go to inverse norm, and we go to area of 0.30. Mu sigma 1, press enter, and we get a z-score of negative 0.5244. And then we repeat the process, but this time we do it for an inv norm of 0.90, and we get 1.2815. I'll round that to 16. Go to a decent number of significant figures. That's my advice to you. And hence we have these inv norm values. So now that we have these inv norm values, I'm going to write them up the top here because we're going to need a lot of space for this calculation. So inv norm of 0.30, we get a z-score of negative 0.5244. And then for inv norm of 0.90, we get a z-score of 1.2816. So that's just double checking 0.52, and I'll make sure those are 4s. And away we go. So we use the z-score formula. And now this is where things get interesting. So with z-scores, z equals x take mu on sigma. Therefore, and I'll just substitute in my inv norm of 30 directly, negative 0.5244 equals, and then what we have is we have x take mu, so of course x in this scenario is going to be 30, 30 take mu on sigma. So, now that we've got this, you're probably thinking, okay, this is looking pretty complex, we have two values there, but don't worry about it for the moment being. I'm just going to bring sigma up from the left-hand, from the denominator on the right-hand side to numerator on the left-hand side, so it becomes negative 0.5244 sigma equals 30 take mu. And we want to repeat this process for the other one too. So let's think about it. Z equals x take mu on sigma. And I probably want to make sigma a little neater. Therefore, Z, in this case, because it's the inv norm of 0.90, it's 1.2816 equals, and it's going to be 80 take mu on sigma. Okay, so now what we do is we simply bring sigma up from the numerator on the left-hand side to denominator on the right-hand side to numerator on the left-hand side. So we get 1.2816 sigma equals 80 take mu. Now, where things get interesting, we want to work out how many standard deviations there are between the value of 30 and 80. How many standard devs are there? So in order to do this, all we need to do is simply say, okay, there are 1.2816 plus 0.5244 there. The negative doesn't matter, and the negative actually shows our value was a little bit off when we said point. In fact, hang on, that should be the inv norm of 20, sorry, in context to the original problem. Haven't I? Yes, sorry, it's meant to be 15%. Okay, so it looks like 30% actually scored under 30 there. I apologise for that. That's my misinterpretation of the question. But in the original question it said 15% scored under 30. That's something to be very careful of. However, I'll change the question a bit. I think I will. I'm sorry about that to confuse you. But again, if you go back to the original part in my video, I came too far to change it, honestly. But sorry, I obviously didn't read the question fully, but it said 15% scored under 30, so if that's the case, you just put the inv norm value of 0.15 in here. In fact, let me change that quickly. Let me bring it to 15% less than. So the inv norm of 0.15, which is revised, again, mu is equal to 0 and sigma is equal to 1, 0.15 gives us a result of negative 1.0364. 1.0364. So it's negative 1.064. So it doesn't really affect us at the moment. 1.06364. Yep, and that means negative 1.0364 there. And in case you're wondering, I'll just resurrect it up here. So we end up getting negative 1.0364. Okay. And now, as I said, we add the standard deviations. It's a good thing I noticed that. It's always good to check your work, but it's that, which is the standard deviations to the right of the mean. And obviously makes more sense now that our value is greater than, so I say less than negative 1. But we add these here, how many standard devs there are to there, and then we add that to the standard devs there. Or should I say, we make both of these values positive. So it's that plus that. And that gives us how many standard deviations there are between 30 and 80 marks. So in this case, it's 1.28 being our 166 standard deviations from the mean, which is the z-score of 80, and then we add it to the z-score of the other one, which is 1.0364. Again, we ignore the fact it's negative, and we get that the total number of standard deviations between 30 and 80 is, of course, going to be equal to 2.31. 2.3181. 2.3181. So now from this we can calculate what the standard deviation is. You're probably thinking, how can we do that? Well, look, we have 50 here. That's the difference between 80 take 30. There's 50 marks spread out over that many standard deviations. Okay, so what does that mean? 50 divided by how many standard deviations there are. So it's going to be 50 over 2.3181 equals sigma. And hence, sigma equals, and we just use our calculator in order to work it out. So in this particular example, if I get my value of sigma here, I go 50 divided by 2.3181, and I get a result of sigma equaling 21.57 marks. I'll just round it to that now. So sigma, and I'll add this to our important thing up the top here list, 21.57 marks. Or we could just say, okay, it's close to 22 marks. Again, it depends on the contextuality. Whether people can get 0.57 of a mark or not is up for debate. In this case, I would just go, say, sigma's 22. But again, we need to still use that reasonably precise value here in order to calculate our mean. How do we do that? We just take one of these formulae and we plug in sigma, and now we only have one unknown, so we can calculate for that unknown. So can you see what I've done here? I've just added how many standard devs there are to the right and to the left. And then I've looked at the range, and I've gone range, divide by how many standard deviations there are, and voila, I have the number of marks in one standard deviation. Thank you very much. And yes, it's technically not solving simultaneous equations. It is a little bit of a cheats way, but it works. It works, and it's very good. Okay, so now I will actually rub this off, and I remember that got my values up here, so I use invnorm of 30. So invnorm of, in fact I should have changed the bottom line. I'll take the invnorm of, I should have actually put that up there, but never mind. I'll use the invnorm of 0.15, which is negative 1.0364, and that equals 30 take mu on the standard deviation we got, which is 21.57. So now we can isolate for mu. So in order to do this, I bring up the denominator of the right-hand side and multiply it by the numerator on the left-hand side. So 21.57 times by negative 1.0364 equals 30 take mu. Therefore, and in order to do this, we can obviously get our calculator and simplify the left-hand side. So 21.57 multiplied by negative 1.0364. It's going to be equal to negative 22.355. And I'll round that to be 3.5635. In fact, yeah, it is 355. Equals 30 take mu. And then in order to solve this, well, I'll go, okay, I'll bring mu to the other side. So therefore, positive mu, because again, it's negative there, so it's positive here. Take 22.355 equals 30, and therefore mu equals, and we just go 30 plus, and I'll wipe out those other calculations now, but 30 plus 22.355, which of course is going to equal 52.355 as our mean. Therefore, mu is going to be equal to 52.4 marks, which of course in context is technically 52 marks. So there you go. We've had a look through this actual example here where we had to look for finding two unknown values at once. And yes, it is challenging. It does require a lot of practice. But again, if you keep practicing and you keep hanging in there and you're able to work through these kind of situations and solve using simultaneous equations, then in the end you will be able to calculate it and you'll be able to get quite a good result. So if I actually check the answers in the back of the book here, it says 21.6 marks, which is, you know, rounded to 3SF there. You know, I don't generally award half marks, so I would say 22 marks there, it's closer to. But, you know, 21.6 sounds reasonable to 3SF. And it also says that the mean is 52.4, which is what we got there to 3SF. So yeah, we were able to do it. That's great. So just remember that process. Watch the video a few times if you need to, but practice, practice, practice using invnorm, understanding invnorm questions, and again, apply things contextually, because at the end of the day, it's that context that you need to interpret in statistics. So that's invnorm part 2. Sorry if it went on forever, but there's quite a lot to cover. It's an interesting topic, actually. One of my favourite in statistics. But again, I'm probably going to leave you be because 36 minutes of your time is probably quite valuable, so I'm going to let you go to sleep or something now. So see you later, everyone.